Hey everyone, welcome. So, have you ever just looked at your phone, watching a 4K video instantly load up over a wireless connection and thought, how on earth are all those digital ones and zeros literally flying through thin air? Well, today we're going to completely demystify this whole process. By the time we wrap up this explainer, we're taking a journey right from the basic physics of radio waves all the way up to building a complete end-to-end architectural blueprint. You're going to walk away with the fundamental concepts you need to create a master stack of steps, basically the foundation to architect literally any type of modern communication protocol. Okay, let's dive right into this roadmap. First, we'll look at the wireless communication problem. Second, phase 1, encoding data. Third, phase 2, wave modulation. Fourth, high-speed constellations and QAM. And finally, we will build out that end-to-end protocol blueprint. All right, section 1, the wireless communication problem, focusing on physical limitations. Let's just start by shattering a pretty common illusion right now. Raw digital data, those microscopic ones and zeros, they can't just magically fly through the atmosphere. They desperately need a physical vehicle. To understand why, we really have to look at physical limitations, and specifically antenna size. Here's the thing. An antenna's physical size absolutely must be proportional to the wavelength of the signal it's transmitting, usually about a quarter of the wavelength. Now, just imagine for a second we wanted to transmit a raw, unmodulated, low-frequency baseband signal, something like human speech, which is around 3 kilohertz. Because low frequencies have massive wavelengths, doing the math tells us the wavelength would be 100 kilometers long. That means to transmit raw human voice over radio, you would need an antenna literally tens of kilometers tall. No way, right? But if we shift that signal onto a high-frequency carrier wave, say 3.5 gigahertz, that wavelength shrinks down to roughly 8.5 centimeters. Suddenly, sticking a miniaturized antenna inside your smartphone makes total sense. But beyond just the sheer size of the antenna, we also have to battle the open air itself. Wireless channels are basically full of thermal noise, signal fading, and just a ton of interference. If you send raw bits into that kind of chaos, a 1 is inevitably going to get corrupted into a 0. So to solve these two massive problems, the antenna physics and atmospheric corruption, we rely on two distinct but highly cooperative processes. First up is encoding, which prepares and protects our digital data for its rough journey over a noisy channel. Second is modulation. This actually embeds that protected data right onto a high-frequency electromagnetic carrier wave that can safely travel through the air. Moving on to Section 2, Phase 1, encoding data, and specifically data processing. Because before our bits ever even reach the physical radio transmitter, they have to be armored up and prepared. Now, this three-stage pipeline happens entirely in the digital realm. Honestly, it's a lot like packing and bubble wrapping a super fragile package before you hand it over to the transit guy. Step 1 is source encoding. This is where we strip out any inherent structural redundancy from raw data to minimize its size. Think of using H.265 to compress a video or zipping up some files. Step 2 is channel encoding, and this is what gives us our error control. And step 3 is symbol mapping, where we group all those binary bits into specific chunks, or what we call symbols, right before they get modulated. Let's zoom in on that second step for a second, channel encoding, and specifically something called forward error correction, or FEC. This is essentially our digital bubble wrap. It injects calculated mathematical redundancy bits directly into the data stream. It's kind of like sending a text message with deliberate strategic typos, like spelling meat with 2 E's and park with 2 K's. If static corrupts a few letters in transit, the person receiving it still has enough context to figure out the original word, without having to text you back asking what you meant. In modern systems, we use incredibly advanced math for this. We use things like low-density parity check, or LDPC, for 5G data channels and Wi-Fi 6, which pushes our data rates right up near their absolute theoretical maximum capacity. We also use polar codes in 5G, which are mathematically proven to be optimal for short control packets. Ultimately, this is exactly how the receiver fixes flipped bits without ever needing to ask for a retransmission. Pretty brilliant, right? All right, Section 3, Phase 2, Wave Modulation Mechanics, looking closely at wave mechanics. Now that our data is all compressed, mathematically protected, and neatly grouped, we need a physical delivery vehicle to carry it all. Now, what's really interesting here is how we actually break down our physical options. A continuous carrier wave really only has 3 fundamental properties that we can mess with to represent our ones and zeros: amplitude, frequency, and phase. First, if we alter the amplitude, the actual height of the wave, we get amplitude shift keying, or ASK. So a 0 is a low wave and a 1 is a high wave. It's super simple, sure, but it's also highly susceptible to atmospheric noise. Second, if we change the oscillation rate, we get frequency shift keying, or FSK. This one is resilient to amplitude noise, and it's actually what's used in legacy Bluetooth. And finally, we can alter the starting position of the wave cycle itself, creating phase shift keying, or PSK. So maybe a 0 is a 0-degree phase shift, and a 1 is a 180-degree shift. This is incredibly energy efficient and honestly forms the absolute baseline for modern digital communications. Which brings us to Section 4, High-Speed Constellations and QAM, focusing on advanced constellations. Look, those basic shifts are great for simple tasks, but our modern apps, they demand gigabits of data every single second. To hit the speeds of 5G and Wi-Fi, we've got to radically escalate our approach. So let's escalate this and dive into something called quadrature amplitude modulation, or QAM. QAM is amazing because it simultaneously varies both the amplitude and the phase of the wave. And the math behind this is just brilliant. Instead of trying to awkwardly vary them directly, QAM splits the carrier wave into two orthogonal sine waves that run at the exact same frequency, but they're shifted by exactly 90 degrees relative to each other. We call these the in-phase component, or I, and the quadrature component, or Q. By independently tweaking the voltage amplitudes of I and Q, the system perfectly produces one single composite wave with a totally unique combined amplitude and phase. Now, if we plot all those valid I and Q combinations that a transmitter can send, we create what's called a constellation diagram. And this is where it gets crazy. Scaling up the number of points on this diagram drastically increases our data throughput. Why? Because a single wave change, just one single symbol, can now represent multiple bits. Just look at this progression. QAPSK gives us 4 points in space, which means 2 bits per symbol. 16 QAM gives us 16 points, so 4 bits per symbol. And this scales all the way up to the cutting-edge standard we're seeing in Wi-Fi 7, which is 4096 QAM. That is 4,096 distinct points in space. It allows us to pack a massive 12 bits of data into a single, momentary little change in the wave. And this matters immensely to your daily life. This massive jump from 2 bits to 12 bits per symbol, that's the exact reason you can download a gigantic 4K movie in seconds when you're sitting right next to your home router, instead of waiting around for hours. So the crucial point to take away from this is understanding the trade-off. It's essentially a really delicate teeter-totter balancing act. As your QAM order increases, those little points on the constellation diagram become incredibly tightly packed together. If atmospheric noise pushes a received signal point even slightly off its target coordinate, the receiver's going to mistake it for an adjacent point, and boom, you've got bit errors. Just notice the extreme ends of our options here. BPSK is incredibly resilient to noise, absolutely perfect for those long-distance cell edge signals. But 4096 QAM, while it's insanely fast at 12 bits per symbol, it is ultra-sensitive. It has very low resilience to noise and demands pristine signal-to-noise ratios. That's why it's pretty much ideal for ultra-short range or clear line-of-sight Wi-Fi 7 setups. The bottom line is, higher data rates just flat-out demand higher signal quality. Okay, Section 5, End-to-End Protocol Blueprint, covering the end-to-end pipeline. We've explored the physics, the encoding, and the modulation. Now let's pull it all together and synthesize these concepts into the ultimate master stack. This is the exact step-by-step workflow of digital data. By understanding this, you essentially have the foundational blueprint to architect any type of communication protocol. It all starts entirely inside the digital brain of the transmitter. Step 1. The raw data stream enters. Step 2. Source coding compresses that stream down. Step 3. Channel coding injects those LDPC or polar redundancy bits for our error correction. Step 4. The bit-to-symbol mapping groups those bits into chunks depending entirely on our modulation scheme. Step 5. The IQ mapper converts those symbolic chunks into discrete in-phase and quadrature voltage targets. And Step 6. The digital-to-analog converter transforms those digital numbers into actual, fluctuating analog baseband voltages. Next, we make the physical leap. Step 7 is up conversion, where we mix those baseband analog signals with a local high-frequency radio carrier wave. Step 8, the power amplifier violently boosts that signal's energy. And Step 9, the antenna radiates that perfectly crafted electromagnetic wave straight out of the hardware and directly into the unforgiving open-air channel. This is where it immediately begins battling noise, fading, and interference. Then, whether it's just across the room or entirely across the city, the receiver's journey begins. Steps 10 and 11. The receiving antenna captures these tiny, degraded alternating microvoltages, and a low-noise amplifier boosts them back up without injecting any extra static. Steps 12 and 13. down conversion and the analog to digital converter sample those voltages right back into the digital realm. Step 14. Demodulation mathematically plots the received INQ points, desperately looking for the closest valid constellation point. Step 15. Channel decoding evaluates all those redundancy checks we added earlier to instantly fix any bits flipped by the air's noise. And finally, step 16. The reconstructed data stream is perfectly restored to the exact ones and zeros that were originally sent out. And there you have it, the absolute master blueprints of modern communication protocols. By understanding how encoding armors our bits and how modulation maps them onto physical waves, you can truly grasp how technologies like Wi-Fi and 5G actually function from the ground up. But, it leaves us with an incredibly exciting, provocative question. As we utilize LDPC codes to scrape the absolute mathematical ceiling of the Shannon limit, and as we push our constellation maps way past 4,096 points, how exactly will the next generation of wireless engineers continue to bend the laws of physics just to keep our data flowing faster? Thanks so much for joining me on this explainer today, and keep questioning how our world connects.